everyone, welcome back. This is the second class, so we will just continue with our review of thermodynamics and probably get into mechanics, review of mechanics, and from probably 2 more classes after we will be going into required gas dynamics. First thing will be one dimensional gas dynamics, that will be 2 more classes from now probably. I think next class we will talk about something physical about the gas, how it talks to each other kind of. We will talk about that next time if we have time, we will see that. So, last time we ended with the laws of thermodynamics, 0th law, first law and second law, and we said that 0th law was needed for talking about something called equilibrium, and we said that if we say thermal equilibrium exists, then we need some property called temperature to be defined for the system, which I will say are equal for the 2 systems if they are 2 of them are in equilibrium with each other. Similarly, if I say mechanical equilibrium, then forces at the surfaces, that is pressure, must be equal between the 2 systems for me to call them to be in mechanical equilibrium across that. And then we said chemical equilibrium is a case where the composition of the gases inside the system does not change. We are interested in only gases, but this can be extended to liquids, solids, everything if you want. We are in gas dynamics, so we will just talk about gases in our case. If there is a system which is in, this is one thing which I missed last time, if there is a system which is in thermal, mechanical and chemical equilibrium, that system is overall called as in thermodynamic equilibrium with another system. If there are system A and system B which are in thermal equilibrium, mechanical equilibrium and chemical equilibrium with each other, then they are supposedly called as in thermodynamic equilibrium with each other. There is nothing that changes as far as thermodynamics is concerned. Okay. And then we went into first law where we said we needed some quantity called energy, and then we said that that property is conserved always. If there is some amount of energy given to the system, then it can use it to do some work, or it can give out some energy, okay, or it can store it within itself. These are the various things possible. We did not put any mathematical expression for it yet, we will do it now. Okay. The next one we said was second law of thermodynamics, where we said we needed some quantity called entropy, and then we said that quantity entropy will always be increasing in the direction of naturally occurring process. Okay. If we go the opposite path in that process, entropy will decrease, and that will not be a naturally occurring process. Okay. So, now we have to put some mathematical expressions for them. So, if I think about the first law, I can easily say that I have some box, some system A, and then some amount of heat is going in, and let us say it is giving out some amount of heat, and say there is some kind of work in, we will talk about that next, and then probably there is some kind of work out. Any other possible interactions currently for our systems? Currently nothing. Why? We are assuming simple compressible substance, where we can do only heat or cool the gas, or we can do PDV work on it. That is the only thing that is possible, we say. So, only this much is possible. So, now we look at this. What do you mean by W in? The surroundings are doing work on the system. That is, let us say I am compressing the gas. What am I doing? Surroundings are expanding, this is compressing. Okay. What is going to happen finally? Surroundings are doing work on the system. What should happen to the energy of the system? Surroundings Okay, let us go to work out. What happens if I say work is done by the system on the surroundings? What should be the case now?
For system it will be negative work, a positive work, and for surrounding it will be negative work.
For the surroundings it should be negative work. If I say that work is done by the system to the surroundings, it is just a convention, I guess. If I say W equal to P dV, I will go back and write it as molar volume if needed. Currently, let us keep it as volume as such. Okay. If I write it like this, what do I mean by this? Of course, when I write this, I have to have a delta W or dW somewhere. One side cannot be dW, on other side nothing, right? Cannot be that. So, when I write this, I am considering I will follow this convention where my system is having a pressure P and it is expanding by volume dV, and this is the work done by the system. Okay. And I am calling this positive work, which means my work done by the system is positive. That is the way I am considering it. Okay. What will happen if work is done by surroundings on the system? Automatically, if work is done by outside onto the system, it is like some piston pressing from outside and the system gets compressed. So, that will automatically give you a negative volume, and that will work if I pick this convention. Of course, I could pick completely opposite convention. As long as I know the convention is the opposite, it will still work. I just have to take care of that minus sign somewhere and it will completely work. We will follow this convention. Okay. We will consider this as W out. dW out is equal to P dV. We will just consider that way. Okay. So, now of course, I can consider a W in and a W out and then find out the net, or I will simply say I will take the summation of all this and I will go to an equivalent system where there is net dW out, okay, net work done outward. If overall the volume of the system decreased, I will automatically get this value to be negative. We will keep it that way. It just comes out to be negative, which means outside external surroundings are doing work on the system. That will automatically happen. Similarly, now I can write this Q in and Q out in a similar fashion, and I will just tell Q in, Q is a heat, amount of heat that is sent in is what I will call as Q in. Now, I will just tell if net energy is going from inside to outside, this will be negative. Okay, that will automatically take care of the direction. So, now I can write overall what should be my energy balance if I think about these two things. These are the two interactions that are possible, heat transfer across the surface and PdV work across the surface. Only two things are possible. Now, the net interaction will be these two together. Anything else missing in my energy balance? Maybe there is energy stored inside. This is the energy E inside my system. Maybe think of the system as myself, and energy can be money right now, easy thing to think about. Somebody gives me money, I could use it to do some work, that is pay somebody, get something done, or I can just keep it in my pocket. So, the system could just take the money from outside, keep it inside in its pocket, or do some work outside. That is the only way you can think about it. Money cannot be thrown away, that is the rule. Similarly, that is the first law of thermodynamics. It says energy cannot be just vanishing somewhere, it has to be present somewhere, it has to be conserved. Okay. That is a simple logic. So, I am going to write, I will just put dq from now on. It actually means q into the system is positive. Okay. That discussion went through up to here. After that, I will just call it q from now on. Net q in is positive. Okay. And I am going to call this dW out is positive. I will not put that out symbol anymore, I will just assume you keep that convention, that is why we spent that 5 minutes in here. So, this is the way we will write, this is your first law from mathematical point of view. Okay. What is happening is net amount of energy taken into the system, how much is stored versus how much is used for doing some work on the surroundings, that is what it says. Now, of course, we can write it as a more common form Cv times dt plus P dV, this is a more common form. What is Cv here? Specific heat at constant volume. How do we define this? Cv is defined as, oops, I have to write it as Cv. Differential change in energy per change in temperature keeping volume of the system constant, that is your specific heat capacity of the gas, okay. That is what is here. And then of course, dW we already said is only simple compressible substance, only pressure volume work is considered. Yes, to be more correct it should be partial differential, we will keep it as partial differential. I could change the internal energy keeping temperature constant and changing its volume. Internal energy, by the way, I have to go back and talk about that next. Any state should depend on two other properties, right. So, it should always be partial derivatives, that is more correct. Okay. We will look at that next, I will go back and explain that one more round. Okay. So, now if I go and talk about second law of thermodynamics, we said entropy is a quantity which always increases, but when we write it mathematically we think of it as there was some net energy interaction with the outside world, and then that energy interaction, if it is irreversible process, then if it is a PdV work it can be reversed. If it is a heat interaction it cannot be easily reversed. Okay. So, we are thinking about heat interaction with the outside world, and then we will say for such an interaction entropy is given by dq by temperature of the system, actually it should be temperature at the interface. Okay. If you go and look at serious thermodynamics books, they will call it, it is at least this, okay. And then they will say for simplicity we will keep it to be temperature at the interface and all that. It is serious mathematically clear, mathematically correct books will talk more about this temperature. It should actually be the reservoir temperature, which is not happening in our any of the gas dynamics problems really. If there is a flow going, there is no reservoir next to it, but we will imagine that there was a reservoir next to it, that fluid element, then we will just consider that particular case, imagine a reservoir next to it and see what it would have done, and then get to these calculations. That is what should be happening. Okay. But as of now we want to get to the mathematical expression final form which I want, so we will just start from here, and then we will say ideally it should be assuming a reversible transfer and all that. Okay. We will not go into too much mathematical details of this reversibility because it is not so important for our gas dynamics, as long as we assume that this math is not wrong. Okay. We will say thermodynamicists have already talked through with this and they are clear about it, we will follow them as of now. So, I can rewrite this along with this other expression, or I would like this one first, then I will go to this form. So, I will rewrite this as I have written this expression, is it in terms of intensive property or extensive property? Why? So I got both the answers, only one of them is right really.
This contains volumes.
Contains volume, easy way to think about it. I have one box with one volume, say take exactly replica of that, put one more volume next to it, total volume will be double. That means it is an extensive quantity. Okay. Same thing with energy. Say I have a box with 1 joule energy gas, take exact replica of it, 1 more joule of energy, put them together, the net gas has 2 joules of energy. Intensive, extensive, extensive. Entropy also same case, extensive. Okay. The whole equation is written in terms of extensive properties as of now. Okay. We will keep it that way for now. So, of course, I can rewrite this as this is the form we will use a lot in gas dynamics. We will see now why. In today's class itself we will see why. Okay. This form is very useful for us. So, I will just put this rectangle around this. Okay. Now, let us say in case I want to think about intensive quantities only for this expression, what should I do? To get an intensive quantity from an extensive quantity, all I have to do is divide by another extensive quantity, right. This is an extensive quantity, I divide by say mass, which is another extensive quantity. So, I will get per unit mass entropy. I have to give a symbol for it, I will use small s. Ideally, I am changing to small c here, not very clear in my fonts, that is the change. Now, I will just call this per mass. This will have units of per mass. What is the actual unit? Joules per kilogram Kelvin. What was the unit of this one? It is just joules per Kelvin. Okay. This has become intensive quantity because I changed the units. Okay. I used this symbol already last class at the beginning. I used this. We said volume per mass. Okay. It is an intensive quantity, inverse of density if you want to think about it. So, this is the typical way we will write if I want this expression to be changed to intensive quantities. Okay. It will just become this simple. Now, of course, I can have per mass basis or per mole basis. Number of moles or number of molecules is another way of I can call it another extensive quantity which I can divide this expression with, and I will get another form of intensive equation. This is one intensive equation, I can get another intensive equation if I want. So, let us call that, I am putting a cap on top saying this is per mole basis. This is molar volume. 1 mole, how much volume will it occupy? Differential of that is this. And if I think about CV, this is joules per mole per Kelvin. This will have a different unit now, joules per mole Kelvin. And this is of course entropy, what is the unit? Joules per Kelvin per mole now. Okay. Entropy units here is joules per Kelvin. Okay. So, here it will be joules per Kelvin per mole, here it will be joules per Kelvin per kilogram. Okay. It is typically mole. If you want, you can think about kilomole, we will come to that when we take numbers, we will do numbers soon. So, this is a very common form which we will use a lot, but I may choose to use one of these forms also in case. Okay. Sometimes I may choose this. Now, there are a lot of other properties which thermodynamicists created, which are useful in analyzing situations, special situations like say a flowing gas. Now I need to think about some more extra quantities. It is not a closed system, it is an open system, mass is exchanging across with the surroundings, then I have to think about some more extra properties. What quantity did they introduce? Thermodynamics? Enthalpy. Okay, they introduced enthalpy for open systems, while they will use E, internal energy, for closed systems. They will go and use enthalpy for open systems, and that is defined by this simple expression. This is the relation. Okay. And of course, I can still define more things. Gibbs was the father of modern thermodynamics, and then he used this quantity, it became Gibbs energy, Gibbs free energy. He called it only free energy, it became Gibbs free energy afterwards. Okay. Gibbs free energy has this form, and this is related to how much, if I talk about change from state 1 to state 2, this will be G1, this will be G2, I am going from G1 to G2, that delta G, G2 minus G1 is the net possible work you can extract from the system if the system goes through this process from 1 to 2. Okay. That is the usefulness of this G. Thermodynamics, what is the use of doing all this? We want to finally find, if I take my gas from one temperature to another temperature, how much energy should I give in, how much will I get out of it, how much work will I get out of it. That is what engineers are all thinking about all the time. Yeah, I give some energy, I give some whatever heat to it, how much will I get out of it. To think about that, thermodynamics gives you this quantity, it will be very helpful for you. This is also called available energy if you go and talk to mechanical engineering thermodynamics people. Okay. We will not talk about it so much, we will still call it Gibbs free energy. Okay. And in case I am doing control volume approach and I want to find closed system, not control volume, closed system. This is for open system, these two will be predominantly used for open systems, this will be for closed system. If it is a closed system, then this is your Helmholtz free energy. Okay. Helmholtz free energy, we will use this symbol, of course different books uses different symbols. Okay. This is just E instead of H there, this is enthalpy, this is internal energy, that will be the only change. Okay. If you think about it in a physical sense, what is really happening is, if I go from state 1 to state 2, I need to supply this energy, plus I have to also supply some amount of energy to increase its entropy, so that the process naturally occurs from 1 to 2. Okay. This is in a way the bribe I have to pay nature to get whatever I want happening. Okay. So, if I give the gas say 100 joules of energy, that will be here, it will not give out 100 joules of energy as the work out finally. Some amount of energy will be lost in increasing the entropy of the gas. Yes. That is the best you can get out of it. You will never get this full amount typically. You will have more losses, but if at all you think about how much can I get for a process, then I have to think about G1 and G2, find the delta G, this is the best I can get from the system. I have to of course think about H1, H2 minus H1 minus T2 S2 minus T1 S1 and all that. Okay. We have to do the whole thing. So, that is the use of these variables. Of course, I can always think about the same convention as I used in this case. Capital S becomes small s if I think about intensive quantities. So, I will go and write intensive quantities here. So, if I think of, I will use mainly this system, I will not worry about F. So, if I want intensive properties, this is per mass basis. If I want it per mole basis, I will put a cap on top of all these quantities, simple enough. and similarly I have G. This is again per mass basis. We will keep this. We will use this H equal to E plus PV predominantly in gas dynamics. It is a flowing gas open system, always needs to be used. So, now we have come to a point where we have used up all the thermodynamics laws. The next thing we need to talk about is about the gas itself. Perfect gas. What is a perfect gas is the next question. Okay. What is a perfect gas? No intermolecular forces. Okay, in a way we can think about it that way. Anything else? Specific heat capacity does not change with temperature, possibly. Any other explanation, any other ways of thinking about it? There is one more. What is it? It follows the ideal gas law or ideal gas equation. Okay. So, what is the ideal gas equation? PV equal to N RUT. Okay, we will think of it that way. Okay, but the way I am going to use it, I will remove this U because I want to write less on the board. I will put this double line R for universal gas constant. This is a constant for all gases, any gas you take in nature, it should be following this number of, what is this? N is what? Number of moles of particles sitting there. Volume is total volume, it is extensive, the whole expression is extensive. What is the extensive quantity here? N is the extensive quantity. Of course, remember both sides should have the same type of quantities. This is extensive, so this should be extensive. Okay. So, this equation should be valid. It has other forms. This is another form where this N is mole density. Okay. N by V is your mole density. It can be written like this if you want, number of moles per unit volume, it can be written like this, or I want to write things in terms of per mass, not per mole. This is per mole, I want it per mass basis. I can rewrite things in terms of that. Then I will go and do this. Remember, this R is slightly different from the other R. This is your universal gas constant. This is called specific gas constant. It depends on which gas we are talking about. It is not all gases. It is a specific gas we are talking about. Okay. So, what is the relation between these two R's? This is universal gas constant divided by molecular weight of that particular gas. Okay. That will be this R. Okay. And rho is my density of the gas. So, this is the link between pressure, temperature and density. If my gas is obeying this, then I will call this gas an ideal gas. Okay. But of course, that is not completely enough. I can call this as a perfect gas equation or ideal gas equation. Now, I have to talk about the remaining things. Somebody guessed here that Cv or Cp, the specific heat capacity, must be constant. Okay. So, we will think about it. Typically, if I think about any property, oh, we have to go back to that, yeah, this is the correct moment to go back to it. If I think about any quantity, thermodynamic state of a system, to define it, how many properties do I need? 2. Why 2? Say I give you pressure and temperature, can you tell me number of moles? Look at this expression. Can you tell me number of moles if I give you pressure and temperature of the system? You cannot. Okay. But can you give me density? Yes, you can give me density. If you know the gas, yes, you can give me density. Okay. Let us say I give you pressure and volume. Can you tell me number of moles for my system? I still cannot. Okay. So it looks like I need 3 quantities, of which at least one of them should be extensive for me to get the complete system, if I am interested in extensive quantities. If I am interested in only intensive quantities, then 2 intensive properties are enough. That is what we saw here. If I give you pressure and temperature, both are intensive quantities. If I give you 2 intensive quantities, that is enough to give me all intensive quantities of my system. I cannot tell you the size of the system, but I can tell you what it will be per kilogram of the system. That kind of information I can give you. That is the idea of this. So we are thinking about how many properties should I give for defining a system completely. Okay. Of course, you have to give its composition, right. We started with 0th law where we said we need pressure, temperature and composition. So we have to give all that, okay, to define things. Of course, I need composition. Of course, I can give you pressure and temperature. If I give pressure and temperature, then I am giving you 2 intensive quantities only, in which case I can give you all intensive properties very easily, but no extensive quantity. If I want to think about extensive properties also, I need to give you somewhere some extensive quantity, say mass of the system or volume of the system, number of particles inside the system, number of molecules, number of moles, something. I have to give you something that relates to the size of the system. Okay. So, but can I give you a state of the system by giving you volume, total number of moles and temperature? Yes, I can. Okay. Look at this expression. If I give you V, N and T, you know R, so only P. If I get P, I have P and T, 2 intensive quantities, I can find any intensive property. If I want to find extensive quantity, then I just take this and multiply with it, I will get all the extensive quantities, right. It is simpler. Okay. So you have to think about this. Now I will go back and look at my energy. If I want to define energy, I have to define it somehow in terms of 2 properties and composition. Okay. So if I am thinking about constant volume kind of systems, I want to think about volume as a key parameter. Okay. Temperature of course is another key parameter for energy, and then remaining things you need will be concentrations. It could be intensive or extensive. I could give you number of moles of each gas in my air, say air is having so many moles of oxygen, so many moles of nitrogen I can give, or I can just tell you 21% of molecules are oxygen, 79% of molecules are nitrogen. I can tell you that way also, mole fraction or number of moles, I can give that also, as long as I have another extensive quantity sitting here. This is another way of looking at it. Okay. So you have to think about it in this specific way. Let us say composition is fixed. Am I giving enough number of variables here? One intensive and one extensive. So if I give you volume and temperature, you will tell me pressure? You cannot. Okay. So ideally I need to give you 3 quantities irrespective of composition. Composition has to be known. Other than that, I need 3 quantities, of which at least one should be extensive, because I am writing extensive, I am interested in extensive quantities. Okay. So I would say I will typically give you pressure. So I will write this instead of this, I will write it like this. Okay. But now we will go back and simplify the problem. We will tell that for my gas, internal energy is not a function of pressure. Okay. I am going to tell it is a function of temperature. Main function is only function of temperature. Okay. Of course, it depends on volume, but that is related to, it is an extensive quantity, that is the idea there. Okay. So, we are going to say I will keep pressure, okay, but I will say my gas does not care about pressure. Okay. Whatever be the pressure, my gas does not depends on temperature the same way irrespective of pressure. Okay. That is what we are going to say. If a gas does this, I am going to call this gas as thermally perfect gas, thermally perfect gas. That is, I am going to write it differently. I will call this Cv, the specific heat capacity per constant volume, is a function of temperature only. Of course, we know the composition exists and the extensive quantity volume also exists, we will not deal with all that right now. We will just tell this quantity is a function of temperature only. If this is the case, then my gas is thermally perfect gas. Okay. If this is the case, then I also can write specific heat at constant pressure will also be a function of temperature only, but a different function. That is why I put a prime there. Some question?
It is depend on the temperature only. So why the pressure, it needs pressure and temperature and all?
I am writing a generalized case here. I am saying to define a state of my system, I need 3 quantities irrespective of, I need composition plus 3 quantities. So, I am picking PV and T, that is what I have done here. Okay. Now, of course, I could have written this Ni as Xi, the mole fraction also, mole fraction of all the species also, that will still work. Okay. Now, I am going to say volume, yes, it is there, that is what is my extensiveness of this quantity, we will keep it that way. Only thing is pressure, I do not want it to be a thing dependent on pressure currently. Okay. I am going to consider gases which are typically independent of pressure. The internal energies relation with temperature is independent of pressure, that is all I am going to say. So, only those kind of gases are called thermally perfect gases. Now, we will go one more step further. We will say if Cv or Cp, the specific heat at constant pressure, if they are constants as a function of temperature, now it is not any general function, it is a constant with temperature. If I say that, then the gas is called a calorically perfect gas. Previous was called a thermally perfect gas, now it is calorically perfect gas. Now I have to define things very clearly. When I say calorically perfect gas, Cp and Cv are constant, along with that I would also call this P equal to RT or PV equal to nRT is also obeyed, okay, by that gas. If I say my gas is calorically perfect, if I say my gas is thermally perfect, then I am saying P equal to RT or PV equal to nRT, along with Cp and Cv are functions of temperature only. Okay. That is what we will have. Now, why are we talking about Cp, Cv so much in gas dynamics? Why? It so happens that for common gases, you had an answer? Tell me.
Gas dynamics, we are dealing with flows, so we need a parameter to define flow like enthalpy and all. So for enthalpy, defining enthalpy, we need a Cp for that.
Okay, enthalpy is given as Cp times T. When is enthalpy given as Cp times T? For which gas? For calorically perfect gas. Okay. In simple gas dynamics, if you go look at most of the books in gas dynamics, they will deal with H enthalpy is equal to Cp times T. They are always assuming calorically perfect gas. Okay. But in real life, no gas is calorically perfect for all range of temperatures. Every gas can be told that for some particular range, say 100 Kelvin to 400 Kelvin, Cp is constant. That kind of thing will happen for most gases. There will be a particular range where it will be a constant Cp, but after that Cp changes. Why? Typically all this time, let us say for low temperatures, the molecules are not vibrating the bonds, but at higher temperatures, let us say I pick oxygen connected with a double bond, right, and the bonds get extended or contracted if I go to very high temperatures. Till that time, that particular vibration is not significant, there is not much energy stored in it, we neglect it and it is okay. But when we go to very high temperatures of the order of 2000 Kelvin for oxygen, it matters. There is significant amount of energy given to oxygen will be taken for vibration of this bond. Okay. So then it matters, at that time we cannot neglect this Cp variation. So I will go back to thermally perfect, I will not use calorically perfect gas in such situations. Typically when we go from regular gas dynamics to high temperature gas dynamics, we will switch from calorically perfect gas to thermally perfect gas. Of course, in this course we will still continue with calorically perfect gas. Okay. Now we will just have to go give some relations between various variables. What is the value of universal gas constant R? If I write a number, I need units for this, unless it is non-dimensional parameter. Okay, I will write whatever I hear first. This is a possible unit which is correct, or I will just say remove this 1000 and 1000. I can equivalently write the unit could be joules per mole Kelvin. Okay, that is also possible units. Okay. I remember it as this, simple enough. Okay. Now specific gas constant, but of course now I have to know what gas it is. Let us pick air. What is the molecular weight of air? That is what I want to correct in this course. Many people will think it is 29, I do not want to use 29. Okay. Use 28.8, if you want to be more accurate, use 28.83 or 84. That is closer to the correct answer. Do not use 29. 29 will throw you off in Cp and Cv values much more. Okay. We will keep this. What units is this? Grams, that is it, grams per mole, grams per mole, but this is not SI unit. So what will I do? I will make this into 10 power minus 3 kilograms per mole. I will write it like this. This answer comes out to be this 288.7 you should check the units also. Per mole divided by per mole goes away, kg is in the denominator, just sticks to the denominator, it is what you should get. Okay. Use this, this is better than, if you use 29 here you will get 286.6, that will throw you off already a little bit. When you want to do extensive variable calculations, you will be thrown off much more. Okay. We do not want that. This is closer to the correct answer for air. Okay. Next variable will be CV. Let us say I want per mole CV. We use the symbol cap for it. Per mole CV. How will I get that? Universal gas constant divided by gamma minus 1. This is the first time I am using gamma here. Gamma is this Cp by Cv intensive or extensive? What Cp should I use here? They should both be same, but they can be extensive or intensive. Okay, as long as units get cancelled, I do not have to worry about it. I can have per mole Cp, per mole Cv, divide them, or per mass Cv, per mass Cp and per mass Cv, divide them, that should all be fine. Okay, think about it that way. For gas air, what is it? For air, 1.4, that is the number for this. Okay. So, of course, I can calculate this number. I have to find what the number is, I do not remember that number. $721.75. I am sorry, I made a mistake here, we will correct it right now. This is kilogram Kelvin, which means I should not put equal to sign here. Okay. I have used 288.7 divided by gamma minus 1 to get to this answer. Okay. 288.7 divided by 0.4 will give you this. I did it per mass basis, per mole basis will be a different number. If you want me to write it again, I will write it. This will give you this number, okay, 721. If I do Cp, this should be gamma by gamma minus 1 times R. This number is 1010.4. Okay. If you use 29 as your molecular weight, you will get numbers that are very different from this. You will get close to 987,000, that kind of numbers you will get. 1003.7 or something is the closest you will get, I think. Okay. So, think about that, use this number, that is better for you. Okay. The next thing we need to talk about is, if I have a process, how will this process occur on a state diagram? That is the main idea of using thermodynamics and gas dynamics. We want to review this thermodynamics so that I can go for any particular flow situation and then look at how my gas is going from one state to other. Is it a particular process? Typically we deal with isentropic process. Of course, I can have some other processes, constant temperature process, constant volume process, I can have different processes. So, I want to go and look at it on the state diagram, that is what we will do the next time, and then figure out what kind of processes will give what kind of curves on them on the state diagram with different axes. We will try different axes. Okay. That we will start with next time, and after we are comfortable with different plots, we will go into laws of mechanics and derivation of mass, momentum and energy equation. That is what we will do next time. See you guys next time. Any other questions you guys have? See you guys next time.